Okay, good morning, everyone. It's my great honor to present our work on the influence of stress concentration and environmental chamber volume on the hydrogen embrittlement susceptibility of L245 pipeline steel Gusfeld. This is Songyan from Xi'an University. I will walk you through our research in traditional five parts. Hydrogen is important for the future green energy system. Pipelines are viable solutions for large-scale delivery, but hydrogen may pose significant safety challenge. The integrity of pipelines, especially their gas weld, is critical. As you know, as you know, welding would uh, welding would introduce defects and stress concentration, which act as initiation sites. So, 会议的那个。就是它变成会议的那个用了。哦，这个怎么做？Sorry. As you know, welding would introduce defects and stress concentration, which can act as initiation sites for failure and the synergetic effect of pressure and hydrogen. Here we list the various aspects of hydrogen pipeline transport. The key point is that a welding defect acts as both a stress riser and a hydrogen trap, making it a critical zone for failure. But current assessment of these defects still largely relies on standards developed for oil and gas pipeline. To address this gap, we have conducted experiments based on the condition highlighted in red here. For welding defects in pipeline, particularly volumetric ones. For example, we can calculate the stress concentration for defects of varying sizes and locations. By integrating this analysis with engineering experience from pipeline operation, we can potentially establish correlations with experimental results. Actually, there are many other equivalent parameters to choose from, but here we selected the stress concentration factor that is familiar in engineering. Here's we have conducted the study. We designed a specimen with a range of stress concentration factor from 1.2 to 4.9, for each condition we tested three pipeline ones. They were carefully prepared by grinding, cleaning, and pre-charging with hydrogen. The tensile test was then performed at 6.3 megapascal in both nitrogen as a reference and a hydrogen environment of 60 milliliter and 580 milliliter. The experimental result in a nitrogen environment is not sensitive to the volume of the environment chamber, so we conducted the experiment in a 60 milliliter chamber. And we calculated the hydrogen embrittlement index as a measure of plasticity loss. Given the notched specimen design and the inability to use an extensometer in the chamber, we represent the index by the loss of reduction of area. The corresponding fracture area was measured using the analysis system. Let's move to the results. First, we observe that a higher stress concentration leads to a lower reduction of area depth. As expected, the hydrogen environment causes a further reduction compared to nitrogen. And notably, a larger hydrogen chamber volume leads to a more significant reduction in depth. And the hydrogen embrittlement susceptibility I doesn't always increase with stress concentration. It actually peaks at a turning stress concentration factor and then decreases. Furthermore, a larger chamber volume increases the susceptibility across all stress. All stress concentration factor values. In smooth specimens, an index below 25% may define hydrogen resistance. This implies a threshold may exist below which which stress concentration has negligible impact to defects. However, test conditions, chamber volume here change the curve, and the associated critical stress concentration factor change. So it's important to establish standards for environment and experiment and engineering if we need further application. And this section is helpful for understanding the concept of turning stress concentration factor. Let's first compare the results from the 60 milliliter hydrogen chamber with those from the nitrogen environment. For the specimen with stress concentration factor of 2.1, the overall fracture topography is similar to that of tensile test fracture in a smooth round bar of a ductile material. And a surgeon dimpled region formed the main crack, shear lips finally at the edge. Well, the results in hydrogen and nitrogen environment are similar. And the hydrogen exposed specimen showed very limited localized cleavage feature. Moving to the fracture surface at stress concentration factor of 3.3. In the nitrogen environment, the specimen also showed extensive cleavage morphology, indicating a predominantly brittle fracture. And in the hydrogen environment, the cleavage area is even larger. Circumferential cracks are a characteristic feature of hydrogen-assisted cracking, observed at the root edge of the fracture surface in specimen tested in hydrogen environment. At a higher stress concentration factor of 4.9, transition is observed. Extensively cleavage morphology almost occupies the whole fracture surface in both hydrogen and nitrogen environments. The result in large hydrogen chamber volume showed more hydrogen embrittlement features. This is evidenced in three key ways. First, by more pronounced localized cleavage feature, and second, by a more severe circumferential cracking, and third, by a microstructure transition at the fracture edge from dipoles to mixed mode of dipoles and quasi-cleavage, and finally to dominant quasi-cleavage. From this, we can deduce that the brittle features are driven by a synergy of hydrogen embrittlement and stress concentration. But when the stress concentration becomes high enough, it in fact overshadows the specific contribution to hydrogen. And this is why we introduced the concept of turning stress concentration factor for engineering. Our discussion ties this observation to establish the theory according Owen's brittle fracture theory. High maximum principal stress at the notch root can cause brittle fracture. But Cheng's stress states surprises plastic slip, allowing the stress to exceed the yield stress without ductile failure. And the distribution of hydrogen in the material is closely related to the hydrostatic stress. And these two figures up here shows the distribution of maximum principal stress and diffusible hydrogen concentration across the notch section. Due to the constraining effect, a higher stress concentration leads to an elevated peak stress, which exceeds the yield stress. This peak stress is not at the notch surface, but in the subsurface region. And crucially, the area of stress concentration and the hydrogen enrichment area are highly spatially coincident. The professor's recent presentation on hydrogen embrittlement mechanism is also useful for the future analysis. Regarding the chamber volume effect, a larger hydrogen environment chamber indeed brings the more brittlement. But second method in hydrogen ingress into material appears to be unattainable in hydrogen transmission pipeline. But a more plausible explanation is that it increases the total frequency of hydrogen collision with the metal surface, thereby promoting the absorption reaction and increasing hydrogen uptake. Inclusion, our study reviews three key takeaways. First, hydrogen embrittlement susceptibility has a monotonic relation with stress concentration, and a critical factor may be crucial for developing defect acceptance rules. And second, brittlement is a synergy of stress and hydrogen. A turning factor is helpful for analysis and assessment of fracture. And third, hydrogen locally promotes cleavage. Larger hydrogen chamber volume further enhanced this cleavage tendency. Thank you for your attention. I'll be happy to take questions.